first. Okay, great. And now that the recording's going, let me reiterate what we're going to do. So the first place we're going to start is looking at sort of prior models of associative learning, and then talk about why the way in which associative learning is implemented in wolves, and the sense of wolves being a nonlinear associative learner. So that's kind of our first place to start. So in terms of associative learning in prior models, I think probably the easiest place to start is just with laying out the concepts of associative learning, and that's been instantiated in prior models. And I think the simplest version of this came from Smith and Yu, where they're basically they proposed a simple associative learning model that just counts up co-occurrence statistics. So the idea would be you've got literally like a matrix where across the top you've got the possible objects you're seeing, and so those are your columns, and your rows would be the different words you're hearing. And on every trial, you're going to get, let's say, typically a set of 2 objects or 4 objects or 6 objects, and you're going to hear 2 words. And so what you're going to do is you're going to increase, in this matrix, let's think of the matrix as each cell in the matrix has an associative weight. So when I hear the word DAX and I'm seeing these 2 objects out there in the world, I increase the weight on DAX in object 1 and DAX in object 4. And then I hear WUG on that trial, so I increase the weight between WUG in object 1 and WUG in object 4. Then the next trial comes, and I get 2 different words and 2 different objects. And so I increase the strength in those particular cells in the matrix. And as I roll through those different trials, what I'm going to get is a weight matrix that is tracking those co-occurrence statistics, right? And if I do that, what you get is the associative weight for essentially the right associations. Those tend to be strongest. And the reason that is simple, because we are always presenting the right words with the right objects. So if you in my example, if you're hearing 2 words like WUG and DAX, and I presented you with objects 1 and object 4, and let's say object 1 was the DAX. Well, on trial 1, you don't know if the DAX is object 1 or object 4, so you just associate DAX with both of them. But if DAX is really object 1, the next time DAX is presented, object 1 obviously has to be present in the scene, right? So it's going to be then on that next trial, let's say DAX and I always forget, and HEEK, right? So if DAX is object 1 is going to be there. Object 4 is not present, but now object 6 is present. So DAX and object 1, the association strength gets stronger. DAX and object 4, it's pretty weak because that's not there. And DAX and object 6 is pretty weak because that was only presented 1 time. So basically, as you iterate over all these scenes that you're seeing, the right statistics just sort of pop out, because DAX always is present when object 1 is present. Okay, so that's like the simplest associative learning model that's out there. Just simply change your weights based purely on co-occurrence statistics. Okay. All right. So that's associative learning, and we can say, how is wolves not just that? So first, let me actually make sure everybody's knows how to kind of run the model, because it's a little bit more complicated than prior models. And we'll just get the model running, and then we'll actually see if we can find. I have some slides to show how wolves is a nonlinear associative learner, but maybe in a live simulation we can actually see this happening. Okay, so to get wolves running, the first thing you want to do, which is what you always do in Cosavina, go to your Cosavina folder and type set path. And then you're going to navigate to your Cosavina DFT projects folder. And there should be Wolf Psych Review 2021 in there. And if you right click on that name, yours should, if you've done this the first time, it'll say add to path, and you want to do selected folders and subfolders. So mine says remove from path because I've already done that step. Okay. And once you do that, then that little folder should become highlighted or engaged. If you then go in there, the Wolves code is divided up into 4 subfolders, which are labeled conceptually, right? So Wolves core, if you click on that, you'll see, let me make my thing a little bit bigger here. In there, you'll see the this cross-sit run, manual run. That's like the BAM file we've been talking about in previous sessions. So that's kind of like your main MATLAB routine. And then you've got the sim file, which is the model. And there's a GUI file, which displays the model when you run it in auto mode, some control buttons. And then this particular model we had in the simulations for the psych review paper, we were simulating lots of different studies. And in one particular study by Kishergis, we needed a bigger field size. And so we created a new sim file for that one study that instead of having like 100 neurons, we had 300 neurons or something like that. So just a bigger version of the model, because the Kishergis study had lots of objects in it. And so we needed more space in our field to accommodate that particular experiment. So if I open the cross-sit manual run file, I'll come back to this in just a second, but basically this is going to be the code that allows us to run a simulation in particular modes and pick which experiment we're going to simulate. Going back to the tour part here, if I go back to my wolves folder, you can see there's an experiments folder right here. If you click on that, that's basically got the experimental conditions implemented for all the different experiments we simulated. Some of these are experiments with kids, some of these are experiments with adults. And basically, yeah, it implements all the details of those experiments, including how the objects and words were presented, the randomization that's present in those experiments, etc. And then we've got the complementary file, which is an analysis code file. So this takes the looking data of the model through time and basically calculates all the behavioral measures that were calculated in the actual experiment so that we can compare the model's behavior to the subject's behavior. Okay, so again, those are organized by the different experiments. And yeah. And then there's some support code, which are just some miscellaneous functions that are used across either the experiments or the analysis code to implement things like calculating the root mean squared error when you compare the behavioral data to the model data and that sort of thing. Okay. So to run Wolves, you would go into the Wolves core, open this CrossFit manual file, and kind of like in simulators before, you're going to have this mode very early in the file, and that's set by default to be auto mode, but you can also set it to be like if you're running lots of simulations to quantitatively simulate data, you can set it to 2 to, for example, run it on a multi-core processor, which is what I would recommend for Wolves because it takes quite a long time because it's a very complicated model. So we usually run that on a high-performance computing cluster. There's some details here I'm going to skip over. The key things are down here. So if you remember from the psych review paper, I actually left this up purposefully. The developmental story that we'll come to manipulates the memory trace parameters. Those can be found in table 4. And so to set the developmental age of the model, you need to set the build and decay parameters to be kind of whatever age you want for whatever simulations you're running. So for example, I've set these up to be 1200 and 800 because I typically demonstrate this model using the Smith and Yu experiment. So we've got 1200 and 800 here, 1200 and 800 in this table. And then my task variable I've set to 1, which is the Smith and Yu 2008-2011 study. Okay, so if you want to simulate, like, let's say the Truswell paper from 2013, you would change the parameters here to be 1000 and 15,000, which are the adult settings from this table. And then you would select the task variable 3 for Truswell, Medine, Hoffrey, Gleitman, 2013. Okay, so that's how you basically pick an age and pick an experiment with this simulator. Once we've done that, then we can hit the run button. And that will pull up the graphical user interface. And then start running that experiment. So this is now running the Smith and Yu experiment. This had 2 objects on every trial. It's a preferential looking experiment. So 1 object on the left, 1 object on the right. And it's going to go through 30 training trials. So I believe, yeah, this is probably the first training trial still. I think the looking, let me just make sure this is right. See if the looking time resets or not after each trial. Can't remember if that's the case. Give myself a moment to have a drink. And I will narrate what's going on. Okay, this is already on to trial 2. Okay. All right, so the you could see I've got an object on the left that's got, let's say, this color and this shape, and an object on the right that's got this color and this shape. You can see the objects just disappeared. That's the end of trial 2. And now you can see the features have changed. So now I've got this object on the left and this object on the right. And yeah, so the model is then attending to an object. You can see at this moment in time, it's attending to the left object. It will then consolidate those features in the working memory of the scene working memory, and then release fixation through this inhibition of return mechanism to look at the other object. So these are these visual exploratory dynamics going on in the front end of the model over here on the right. You can see where the model's looking through this looking time window. So the red color is looking to the left object over time, and the blue color is looking to the right object through time. So you get the kind of looking history of the model in this plot. If you then look over on the far left, you're going to see that in addition to seeing those two objects out there in the world, the model is hearing words in the word layer here. So word 16 just turned on. I have no idea what particular word that is, but word 16, word 18 just turned on. And whenever the model hears a word, while it's looking at a feature, you can see we're going to get these intersect. When it looks to a feature, you get these horizontal ridges. And when it hears a word, you're going to get vertical ridges. And whenever those co-occur, you get these little peaks in these word feature fields, which is the association of that particular word with those particular features. And early in learning, the model is pretty much acting like a simple associative learner. So when those horizontal ridges meet vertical ridges from the word, it'll build a peak and form an association. And associations in dynamic field theory are memory traces. So it's going to leave a little memory trace in these Hebbian word fields over here on the far left. And I don't know if you could see that on your screens, but you're starting to see some light blue spots in these memory trace fields. Okay. So early in learning, it's doing pretty much exactly what I described that Smith and Yu associative learning model does. Okay. Every time horizontal ridges, meaning every time it's attending to an object out there and its features, co-occurs with hearing a word, which is the vertical ridge. When those co-occurrences happen, then it builds peaks and forms a memory trace. And the memory trace you could think of as a weight in a neural network. So memory traces are going to vary in strength between 0 and 1. When the peak is present, basically what's happening is you're going toward an attractor at a weight strength of 1, and you're going to get there depending on the build time, so that tau build parameter. Okay, so you're going to have an exponential growth toward a memory trace strength of 1, but you're going to do that very slowly, right? Because the tau build is 1,000. By contrast, I think the tau on the fields is 5. Okay, so that means it's going to take, what do these numbers mean? So this is, these numbers are related to a concept called relaxation time, which is how quickly you move to an attractor or toward the attractor. So you could kind of loosely think of it as if my tau value is 5, in 5 time steps, I'm going to get pretty close to the attractor state. If my tau value is 1,000, it's going to take me 1,000 time steps to get close to the attractor state. Right? So I'm going to get to the attractor state much quickly for a tau of 5 than a tau of 1,000. So what that means is when the peak is present, I'm going to grow my memory trace strength by so much, and then the peak's going to go away, and then I'm going to start to decay very slowly. And then the peak comes back, and I'm going to grow it a little bit more, and then the peak's going to go away, and I'm going to decay. Okay, and so I'm going, if you looked at the memory trace, you'd see these little sawtooth patterns. They go up when the present peak is there, and they go down very slowly when the peak isn't. And then they go up when the peak is there, and then come down very slowly when the peak isn't. So that's very similar to the growth of like weight matrix in an associative learning model. So far so good. We're kind of like almost counting co-occurrence. The difference is it's not one co-occurrence on a trial. The co-occurrence depends on where you're looking and how you're attending through time, right? So if you think about what I said earlier about the Smith and Yu associative learning model, on a particular trial, I get object 1 and object 4, and I get DAX and WUG, right? And I just increase my weight strength by a fixed amount for that one trial. In wolves, you can already see something different is going on, because if you look at the looking time here in the plot, looking time varies depending on how well known the object is. And that means the particular associations I form on every trial depend on which particular objects I look at and which particular words I hear at those moments in time. Instead of just slotting in, I increase these 4 cells in that that matrix I described earlier. Now we're increasing the strength of associations based on literally the dynamics of looking, attending, and hearing words, and how those things come together through time. Turns out that's pretty similar to counting co-occurrence statistics. But of course, we could think of ways to, like, let's say I bias your attention. Let's say I make one of the objects more salient. Now, suddenly, if I'm attending more to that object, I'm going to associate those features with maybe both words, right? Because I'm attending to that object more, going to have more associations with both words. And the associative learning in that context might differ slightly. So we could start to see ways in which maybe we can have the associative learning in wolves start to diverge from the associative learning in, say, Smith and Yu. Okay. The other way in which, I'd say the more important or dramatic way in which this type of associative learning differs from the Smith and Yu associative learning comes from that nonlinearity part. So let me go over that using a slide from our paper. Maybe. Okay. Everybody see that okay? I can't see you anymore, so hopefully you can. And let's see, okay. So what you're looking at here, and I talked about this in the presentation, but let me go kind of through it, and maybe if you have questions, I can address your questions. So the top panel shows a schematic of the model when it's attending to the red item on the right. And we're just looking, let's say, at the color field here. And that has presented a horizontal ridge here in the word feature field. And we're hearing the word BOSA, so that sends a vertical ridge here. And you can see the model's built to peak at the conjunction of BOSA and red. And that peak leaves a little memory trace, which is very hard to see, but this faint light blue memory trace here in the memory trace layer shown in this panel here. Now, what I'm showing you in the middle panel is the memory trace building up from the first 5 trials to 10 to 15 to 20 to 25 to 30. And importantly, we built the feature word associations in this model so that if you had these hotspots along the diagonal, those were actually the correct associations. That was just easy for us to say, yep, if the model gets a diagonal, it's learned the correct word object associations. In the bottom panel, and this is the kind of key panel, what I'm showing you is I'm presenting the same two objects, the red circle and the blue square. And at this moment in the simulation, the model is once again looking to the red thing, happens to be on the left in this example. So it's looking to the red thing. That sends a ridge, a horizontal ridge through the word feature field. And it's also hearing the word BOSA, just like in the panel above. But what you can see is there's no peak formed at the conjunction of BOSA and red in this field. Instead, there's a peak down here. And what's going on there is the model is hearing BOSA, and it's recalling that BOSA is actually the blue thing. So it's actually building a peak at you could say the semantic meaning of what the word BOSA, or the feature that's associated with BOSA. And that prevents a peak from building where the ridges are conspiring as above. So Wolves actually has the ability, once it knows what a word means, to prevent erroneous associations from forming. And simply put, an associative learner won't do that. An associative learner will just blindly put a peak here and leave a trace in its associative memory. Okay, so we sort of refer to this as it's nonlinear associative learning. Wolves has the ability to block erroneous associations. Okay. So let me pause there and see if there are any questions about that. Okay, so far I've gone through kind of key comparisons between associative learning models and Wolves. I'd say the two things I mentioned there were, Wolves is unpacking this time scale of active looking and learning, right, which isn't present in the other models. That gives us the ability to probe things, let's say, like attentional salience. And then the second difference I mentioned is that associative learning in Wolves has this nonlinear quality, which isn't present in associative learning models. So then I guess the next step in our tour here was to then think about the developmental story and how that feeds into this associative learning mechanism. So if everybody's happy, we'll go on to that next step. Okay, so I'd say probably the best illustration of the developmental story comes in the paper where we simulate the data from Haley Vlock and colleagues. And so what I'd like to do, Matt, maybe as illustration of the developmental stuff, is to turn to that. Let me just say, first of all, concretely, again, what are we changing developmentally in the model? So let me pull up that table 4 again. And what you can see is we are primarily changing the tau decay parameter. So the tau decay parameter, let's sort of put that into words, what that means. So if I have a tau decay of 700 versus 15,000, what that means is I'm going, when I talk about decay of a memory strength, I take the strength of the weight, let's say, and that's going to then decay exponentially towards 0. So go back to 0. And the tau parameter says how quickly I do that. So a tau of 700 means I decay more quickly than a tau of 15,000. Okay, so it's going to take me 700 time steps to get to 0 versus it's going to take me 15,000 time steps to get to 0. You can kind of think about it that way. Okay, so that means early in development, we're saying decay happens quickly. Later in development, we're saying decay happens more slowly, which, maps onto lots of ideas in the developmental memory literature that kids have a crappy memory and, adults have a much better, more resistant to decay memory, right? So conceptually, that was the idea. And then let's see what consequences that has. So if I go to the this part of, I'm going to leave it in this mode so I can see you guys rather than going to full screen mode. So Haley Vlock had some really interesting data where she's using the same cross-situational word learning paradigm that I'm simulating in the background right now. And what she did was an interesting manipulation of varying when the targets were present across trials. So you can see in block 1, she's going to have one object that is always present from trial to trial to trial. So this little rattle thing. And that's going to be the masked object. And you can see on the next block of trials, it's the little flower is the masked object. And then whatever this thing is, like a house, and then a little bridge or whatever. And then other objects are going to be presented in interleaved fashion. And those guys are going to be presented across blocks. So you can see this maybe submarine thing is presented once in every block of trials. And what they were interested in is, do kids learn from masked exposure better or from interleaved exposure better? And, of course, what is being manipulated here are the time scales of presentation, right? The interleaved, you will go up a little bit the first time it's presented and then decay in between and then go up a little bit more and then decay in between and then go up a little bit more, decay in between. For mass, you can imagine you go up, you don't decay much, you go up, you don't decay much, you go up, you don't decay much. But then, of course, if that is presented in block 1 versus block 6, you might have big decay if it was presented back in block 1. So there's interesting dynamics in how memories decay by comparing masked versus interleaved, basically. And what she found was an interesting developmental shift. So the blue bars in these figures are from the empirical data. And what you can see is that 16-month-olds are above chance on the masked objects, but not above chance on the interleaved objects. 20-month-olds are above chance on both masked and interleaved. And then older kids, 47 to 58-month-olds, are above chance on both, but actually do better on the interleaved. So she talks about this interesting, almost kind of U-shaped developmental pattern, right? Where you're switching from masked to interleaved. And the question is, how do you understand what's going on there? And we've found that by varying this tau decay parameter, we were able to account for this kind of developmental crossover. So what you're seeing here is the memory trace strength for word object pairs presented in the different orders for the masked objects and the interleaved objects. And then we're varying the tau decay parameter across panels here. Okay. And the way we sort of conceptualize this is, we're at the end of training during test. We put this dotted line here and said, okay, let's just assume anything with an association strength greater than this dotted line value, you're going to recognize at test, right, and be above chance on that object. But items that are below this memory trace strength are going to be at chance or below chance, right? And so what you can see is for the masked presentations, there are some objects that you're actually doing really well on, because those were the ones that were presented in block 6. And those have a really high memory trace strength, because you basically saw them and built a memory strength, saw them again, saw them again, saw them again, saw them again, and you haven't yet decayed. So really strong here, whereas the interleaved ones are just sort of gradually and slowly building up. So the idea was that, and we showed this in the simulations, that kids would do well on some masked words at test and do quite well on those, and that would drive performance above chance on the masked trials, but they would be at chance at interleaved. When we changed tau decay to be now to decay slower, so less memory loss, now you can see the blue line generally just kind of shifts up, right? So if you compare this blue line to this blue line, it's basically kind of an incremental boost across the board. And in general, masked also improves. And if we take this kind of cutoff value here, you can see now you're going to still do better on masked, but you're going to be above chance on interleaved as well. And then as we change tau decay even more strongly, you can see now interleaved is doing quite well across the board for all these different words, whereas the ones that were presented in a masked way early on, you don't have a very good memory of those. So in general, you're going to do well for all the words for interleaved, but you're going to lose some of those masked pairs that you encountered in block 1 and block 2. So for us, this was a nice explanation of a complex pattern in development by simply changing one thing, which was that tau decay parameter. And it captured a complex pattern of developmental change with a single change in parameter value. Okay, so that's kind of the story. Now, the question you asked at the beginning was also not just about what's the story, but how did you arrive at that story, right? And how do you tune a model to do this? And I'd say, conceptually for us, we thought, when we looked at the literature on changes in memory, we thought this tau decay parameter was a good target for a parameter that might capture developmental data. So it's kind of a priori reasons to think about that memory might change in this particular way over development. So like Yuko Mutakata did some work on kind of these types of memory decay parameters back in the late 90s. More recent models have also looked at sort of these tau decay or memory decay parameters. Like Linda Smith's done some work on related models. And so we had a kind of a priori reason to target this particular parameter. And then, yeah, the rest is honestly just quantitative simulation. So we literally set up this paradigm that block from these experiments. So that's, you know, literally, I think, I don't know if it's going to let me, actually, I'll do it in the other version of MATLAB. So first thing we had to do was program up the block task from those experiments. So if you go into the Wolves experiments code, you can see there's several block slight variation differences across these different experiments. But, you know, when you open those up, then you've got, you know, a programming task to do to actually implement all the different, you know, the masked and the interleaved, and randomize your objects and presentations and everything like she did. And then we wrote the code to do the analysis like she did. So now we've got the experiments programmed up. And then what we did was we just varied the tau parameter across a full range of values, and took the model data and the behavioral data as we varied that tau parameter, and found which one fit the data best. And there you go. That's what we published. Now, what if that hadn't worked, right? What if we didn't effectively come up with a good explanation for Flock's data? We probably would have moved on to a couple other developmental hypotheses we proved in other work. Like in previous Friday tutorials, I've mentioned the spatial precision hypothesis, you know, where we're increasing the strength of excitation and inhibition in different fields. So we probably would have moved on and explored how that modulates performance in the model. And that's actually something we're actively doing for other projects. So we've got some simulations of some infant data where we made some changes to excitation and inhibition in the working memory field. And I think the inhibition of return field was also involved in that. So you know, that's a matter of, I'd say, first you have to have a good, you know, conceptual understanding of how the model's working to say which fields might be involved in this particular behavior I'm trying to model. And then, you know, running simulations of that particular experiment and seeing how close are you to the data. And then saying, well, if I manipulate this parameter, it moves the, you know, literally the behavioral output of the model this way, or, you know, changes the behavior in this way. What is that telling us in terms of how I understand the model works? And then we're iterating on parameter changes to try to understand basically how the model works and how that pattern in the data, where that might have come from. So I think as you manipulate parameters and run simulations of data, you start to get a better understanding not only of how the model works, but what's going on in the data to create that pattern, right? Because you know, one of the interesting things that can happen is, like, if I go back to the you know, this complex curve, right? You can see both masked and interleaved. Your memories are getting stronger as you forget less, right? Both curves go up, but we didn't necessarily expect a priori that one curve would go up faster than the other. And that was the interesting property that we found in these simulations, right? So we thought this might be a good parameter to manipulate. We thought maybe that will capture the data, but you know, to be honest, we didn't necessarily, you know, fully expect that one curve would rise faster than the other. We hoped it would, right? Because that, of course, would provide a nice explanation of the data. But you really need to actually run quantitative simulations to see that effect emerge. Okay, so I did nonlinear, I did comparing models, I did the Development. Yeah, I guess in response to Evelina, your question about did we run into things that were particularly hard to model, or any real challenges or surprises as we were doing this work? This was one of our pleasant surprises, I would say. Another real pleasant surprise, I would say, was I think I mentioned this in the presentation online. So we went in and simulated these data from Trueswell. I'll go back to, so he did this experiment. You get, oh, look, a zood, and you have 5 objects, and you have to pick one, and then later, oh, look, a zood, and you have to update your hypothesis or not, right? And you can see bear is the only thing that's present in both of these displays, so zood must be the bear, right? And the idea was, this kind of key data for him was, or for that group, was that if you thought it was hand on this first trial, and you only form that one hypothesis, then when you get to this trial and you hear zood, hand is no longer present, so your hypothesis must have been wrong. And the claim was that you didn't retain any knowledge about the other 4 objects. So that if you were previously incorrect, now on this trial, you should be at chance levels, which is 20% in this experiment. And that's what they found. So that was a real challenge because, associative learning models would say, well, maybe you thought hand was the zood, but you maybe made some at least weak associations between the other objects and zood. So why aren't you above chance here? So we thought this was going to be really tricky to model. And this is one of those cases where we had already captured a number of adult studies at this point in our history of this model. So Ajaz went away and programmed up the Trueswell study. And the first time he analyzed the data, it fit this pattern perfectly. And we were like, how the heck did that happen? And he said, well, it turns out there's a really simple explanation, which is in the dynamic field model, in order to form multiple associations between zood and these objects, the timing has to be right. I have to have enough time to look at different objects while zood is repeatedly presented, right? Because it's all about those horizontal ridges matching the vertical ridge and coming together to form a peak. And he said, when he looked at the data, it turned out participants in the study tended to respond after a single look. These are undergraduates. They're trying to get through the experiment as quickly as they can. So they hear, oh, look, a zood. They look somewhere, they pick it, right? So that led to the prediction that if we forced participants to study the display and really look around, right, that we might be able to shift this bar and show that there is actually multiple associations being formed when they are allowed to make multiple looks. And so that led to simulations of wolves when we forced wolves to not respond until after a delay. Then it made multiple looks and formed multiple associations. And as the blocks went on, eventually it was showing above chance performance, even when it got it incorrect previously. And then we ran an experiment where we forced undergraduates to sit there for 6 seconds and look at multiple objects. And they showed the same pattern. They were also above chance, even though they got it incorrect previously. So that was a nice example of kind of a surprise from the model, right? We thought this was going to be a really hard experiment. Once we programmed it up, it led to new insights about the timing and co-occurrence of these things, which then led to a nice new prediction, which we've tested. In terms of difficulties, I would say, yeah, the biggest difficulty is that I can illustrate that right now. We've been now talking for almost an hour, and the model is still running one, it's still going through the Smith and Yu experiment, right? So now we can get this to run faster by turning the graphical user interface off. And on our high performance computing cluster, we can actually do something like running 96 participants simultaneously. So that's good. But, this is literally a real-time neural model. Every time step, I think, is 5 to 10 milliseconds, right? And there's a lot of calculations involved in every time step because it's a complicated model. And so that means quantitatively simulating data takes a long time. And when you're trying to, I would say do it carefully. Reviewers are going to want to know how many parameters did you change, right? And so we can realistically only explore so many parameters, right? And once you fix the parameters for, like, let's say the Trueswell or let's say the Smith and Yu adult experiments, once you fit those data, it's great if that accidentally fits the Trueswell data as well. But of course, there's no guarantee. And so then sometimes you have to go back to you go to the Trueswell experiment, you have to change a couple parameters to fit that experiment. And then you're in this place where, should we go back and see if the Trueswell parameters capture the Smith and Yu data? So you can get into these cycles of trying to find the right parameters that fit all the adult experiments. And that's just a lot of time, right? It's just running we're fitting some data right now and exploring parameters for another paper. And it literally takes, we're varying 4 parameters, I think. And it's ultimately going to be like a month and a half of continuous simulations. So that's, a real challenge. These are not easy models to work with. Yeah. Questions or thoughts?
Maybe a follow-up question. I think what's really fascinating here is that you first use, is the very architecture of the model and the different fields. So you first use space to form the association, but then the association are formed in a feature word or feature label field.
Yeah, right.
So you detach from space. And this is, I think, where the normal associations live, but that space is really, so maybe with these other models, to what extent is the architecture that's the, not what, I don't think it's really a question, but it's, you said that you don't know other models. Do they have very similar architecture? So I think this architecture is the fascinating magic that happens in the thought process of assuming, depending on the experiments, or how does that change, or is this something already quite settled?
Yeah, I think the inclusion of space definitely makes it different from other models, because of course most models are going to skip over that step, and of course we're interested in looking dynamics, so we don't really want to skip over that step, because as you distribute your looks through time, that changes what you learn, right? So, and we also want to ultimately relate word learning to not just visual exploration in this simple space, which is like a preferential looking task, but like we'd like to get it to be real space, right? And that's kind of what we're working on now, is trying to extend the concepts here to like, let's say a robotics platform, right? Where the robot now can look all around and has to form a representation of really a real scene representation of which objects are where, right? Even though some objects aren't currently in view, and be able to handle those transformations and say, oh yeah, there was that, the DAX that was over here out of my, visual field. How do I then plan a eye movement, or eye and head movement really, to when I hear DAX, look over here and say, yep, the DAX is over there. And of course, that's a much more challenging sense of space, right? But ultimately, that's what kids and adults have to use to learn words. And we think some of the developmental changes in that scene representation are critical for the development of early word learning as well. So, it's not just we'd like to capture more data. We think that, changes in that scene representation system are really important for early word learning as well. I think the model's finally done. Is that right? Maybe. Yeah, the question I didn't quite get to yet was about how we merged the visual exploration and space model with the word object learning model in this case, and more generally, how do you merge, prior models together, and it's a very complicated question. We are actually in the process of working on that question in another grant I have, which is related to the word learning stuff I just mentioned with the robotics project. But basically, we're trying to think about, we've had 30 years of dynamic field theory and building models of different functions. Would it be possible to bring those all together into kind of one integrated model? And we're sort of challenging ourselves to see how far we can get with that idea. And yeah, it's definitely not an easy thing to do. I would say this model already is pretty exciting in that I can point to, like I would say we presented it in the psych review paper as the integration of two models. But in fact, we started with this contrast and working memory interaction. That was what we used to call the 3-layer model. And the third layer is the mutual inhibition between these two layers. So it still is the 3-layer model, but we only showed 2 of the layers really. So we started, that was a whole line of work on visual working memory. And then on this side, spatial working memory. So we had kind of early models of this, early models of this. When the model we talked about last Dynamic Friday tutorial was the Iowa model, which lives up here in the spatial attention layer, with some pieces of it dropped off for simplicity. Then we had a model that put the visual field and attention and working memory together. So that was another paper. So that kind of bringing this into full focus. And then we had another model that did all these pieces. Meanwhile, we had models with Larissa's group over here, which is the word object learning model. Yeah, and then we put all those. So it's really 5 or 6 models that we put together in this Wolves paper. But we didn't want to push the envelope too far. So we said it was 2. Yeah, so I think that is at least a demonstration proof that it's possible. But yeah, you could then ask the question, how do you do that? And that's, of course, yeah, you gotta like make a proposal for how these fields all couple together. You gotta build a model. You gotta say, where might we find behavioral constraints for how this model behaves? Which experiments in particular? Let's see if we're in the right ballpark. See if we can get all the fields to play nice together. That's always going to reveal new things about the concepts that you're using, right? Yeah, and then you get into the more practical side of running simulations and that sort of side of things. So, but I think the concept is an important one in cognitive and developmental science, because we don't always try to integrate stories together. And I think that's really important, because sometimes stories are in one domain are answered with one type of model, and in another domain with a different type of model, and a third domain with a different type of model. And ultimately, those models might not be compatible at all with each other. And so if we want to be sort of a cumulative science, I think one way to try to do that is to build these integrative stories within the same theoretical framework, because of course that integration is going to be easier if we use the same language, right, across these stories. Okay, I'm going to stop sharing and stop the recording.